Hi everyone, happy Thursday to you all. Today we're going to talk something about recursive sequence. So what is the recursive sequence? The recursive sequence is the term who can define by its previous term. So no matter it's Fibonacci sequence or the factorial, in order to find the next term, we have to know what is the previous term. And based on the definition, it looked pretty straightforward. But if we took a look about the question below, take a glance about the question and think about it. How could you solve it in terms of using the sequence? You have 3 seconds to do so. Already, the time is up. So if we take a look about the question above, we can see that the question itself satisfies fx is equals to f1 minus cosine x. So let's x is equals to 1 minus cosine x, because this is a satisfaction. But if we take a look about satisfaction, we can figure out that there is an x appears in 1 minus cosine x, and we can replace the argument x in terms of using 1 minus cosine x. So the equation can be rewritten as fx equals to f1 minus cosine and 1 minus cosine x. And if we rewritten this equation all the way down to infinite terms, we can find a specific relation. We can call that the recurrence relation, which is a sub n equals to 1 minus cosine a sub n minus 1. And because it's a sequence, we have to define its first term. So let's assume the first term is a sub 0. And the a sub 0 is equals to x, so the x can be any real numbers. It doesn't matter what is the first term. Okay, so let's say that this was the recurrence relation we found in here. And let's use the recurrence relation we found in here and take it back to the original satisfaction. So f a sub 0 is equals to f1 minus cosine a sub 0, because the original satisfaction says down here. But if we figure out by using the recurrence relation we found in the previous page, and we can also find here is another way to present 1 minus cosine a sub 0. It is f a sub 1, because f a sub 1, based on the recurrence relation we found in the previous page, it also equals to f1 minus cosine a sub 0. And if we just, in terms of using the recurrence relation about that, we can find that f a sub 2 is equals to f1 minus cosine a sub 1. And 1 minus cosine a sub 1 is just originally equals to the original satisfaction of a sub 1. So we can figure out the specific relation about that, which is all the term is equals to the same function above. So f a sub 0 is equals to f a sub 1 and equals to f a sub 2 and equals to all the way down to f a sub n. So those equations are all the way the same. And let's take a limit of that. So we can just assume that f a sub 0 is equals to the limit when n approaches to infinity of f a sub n. And if you took a look about the limit, about the relation, you can think about that. What could be the final answer about f a sub 0? F a sub 0 over here. We all expected that the f a sub 0 is equal to 0, because the question itself says it continues at x equals to 0. And as we all know that on a continuous function, the limit of the function is equal to the value of the function itself. So the next step will all explained by Tim.
Alright, thanks Lucas for talking for something about recursive sequences. So now in order to prove the sequence is convergent, let's talk about it is bounded and monotonic. Remember, those two conditions are required to prove that a sequence is convergent. So now, because our recursive sequence is defined as a sub n is equal to 1 minus cosine of a sub n minus 1. So this means we need to say it is bounded. And because of the function of cosine has a range of -1 to 1, which means every cosine of t is between -1 to 1. So the expression is also bounded because 1 minus cosine t is obviously between 0 and 2. So now we can use our recursive rule, and therefore for every term after the first term, because the first term a sub 0 is any real number. So every term after the first term, we can say that 0 is less than or equal to a sub n is less than or equal to 2, which proves that this sequence is bounded. And now as long as it's bounded, let's talk about its monotonics. So the sequence is monotonic. We need to say that it is always increasing or always decreasing. So it is not like usual sequence written in the original form like a sub n is equal to f of n. This sequence is a recursive sequence, so it is written in some form like a sub n is equal to f of a sub n minus plus 1, something like that. So for a recursive sequence, we can compare the two consecutive terms. For example, we can let a sub n minus 1 equal to x, then a sub n is equal to 1 minus cosine of x. So now we can compare the difference. The reason we need to compare the difference because we can find that is the difference always increasing or always decreasing in order to say the sequence is monotonic or it is not monotonic. So we can define a function here. So we can use a helper function g of x since f of x is used. And now we can prove that the sequence is monotonic decreasing because g prime of x is equal to the derivative of g of x, which is sine x minus 1. And because sine of x is always between -1 to 1, so we can say that sine x minus 1 must be less than or equal to 0. So this proves that g of x is monotonic decreasing. So g of x is monotonic decreasing. We can find g of 0. 0 is the smallest n term. So we can plug in 0 and it is equal to 0. The result is equal to 0. So because x is greater than or equal to 0, we can prove that g of x is less than or equal to 0 because g of x is monotonic decreasing. Every term after 0 must be less than or equal to 0. So for n is greater than or equal to 2, because when n is equal to 1, we cannot make a difference. So a sub n minus a sub n minus 1, which is the difference, is g of a sub n minus 1, and is less than 0. Therefore, we can say that a sub n is less than or equal to a sub n minus 1. That's the definition of monotonic decreasing. So now as long as the sequence, is both monotonic and bounded, we can use the convergent definition of a sequence to say that the limit as n approaches infinity of a sub n is equal to L. And so we can now find the limit because we want to know what number L is. So because this sequence always fits the recursive rule, L as a term, it also fits the recursive rule. So we can write L is equal to 1 minus cosine of L. And by rewriting the equation, we can write L over here. So it becomes this equation. And this is the same as, remember, the g of x we define at top of here. So we find that it is the exact same thing. So we can use our g of x again. We find that g of L is equal to 0. And through our observation, through the transcendental equation, because we cannot directly solve it. So we don't have a calculator. So g of 0 is 0. We can, through observation, we can do that. And is that the only solution? Because we can, through observation, we can get g of 0 is equal to 0. The answer is yes. Because just trust me, because g of x is always monotonic decreasing. That means after x is equal to 0 as the value changes, it can only decrease. So that's why at L is equal to 0 is the only solution for that equation. So now we can drop to our final conclusion. Because using the limit composite rule, we can say that limit as n approaches infinity of f of a sub n is equal to f of limit of n approaches infinity of a sub n. And this is equal to f of 0 because remember we given that function f of x is continuous at x equals to 0. And therefore, from the previous as Lucas did, we can also get like this thing is equal to f of a sub 0. And because f of a sub 0 and this thing is also equal to f of 0, we can get like f of a sub 0 is equal to f of 0. And since the first term was any real number, remember a sub 0 is any real number on a thing. If you can write this thing is a sub 0, this thing is a sub 0, but all of the function values should be same as the function value as x is equal to 0. So which indicates that this function must be a constant. Alright, thank you all.